Hi all, in this video I will teach you about Poisson distribution and also two derivations. One is to find the mean and variance of Poisson distribution. The other is to show that Poisson distribution is a limiting case of binomial distribution. Now what is Poisson distribution? It is a limiting form of binomial distribution when n approaches to infinity. And what is n? It is a number of trials. When n is very large and p being the probability of success is very small in such a way that NP tends to a finite constant, say lambda. It is a discrete probability distribution modeled for rare events whose probability is very small, that is, the events are very rare to occur and where n is not known. The PMF of Poisson distribution is given by f of x lambda is lambda raised to x e raised to minus lambda by x factorial, where lambda is the mean given by this equation lambda is equal to NP. You probably have to by heart this result because we will be using this equation whenever we want to find lambda when n and p are given, where p is the probability of success which is very small. Usually if p is less than 0.1, we consider that problem to be solved under Poisson distribution. X is the number of success where x is 0, 1, 2, 3 up to infinity, whereas in binomial distribution our x varies from 0, 1, 2, 3 up to n. Some examples are number of errors committed by a news reader, number of wrong telephone calls received in a day. And the cumulative distributed values capital F of x lambda is nothing but adding all the probabilities up to x starting from 0. 0, 1, 2, 3 up to x will give you the probability capital F of x lambda, which is directly available from the tables. Now let us proceed with our first derivation. Show that the mean and variance of Poisson distribution are the same. You know the PMF of Poisson distribution, and this is the formula for expectation. Now you have to replace p of x by this equation and then put the limits of x. X is from 0 to infinity, but x factorial is x into x minus 1 factorial. Replace x factorial with that expression. Now cancel this x and x here. So after cancelling, the limits of x will now change. So instead of x equal to 0 to infinity, it will now become x equal to 1 to infinity. Since e raised to minus lambda is constant, because here x is the variable, I am going to take that outside the summation. Now I am going to expand the summation. After expanding, you will get this equation where 1 minus 1 is 0 factorial, which is nothing but 1. And you know that the expression inside the flower bracket is nothing but the expansion of e raised to lambda. I am going to replace that by e raised to lambda. After simplifying, you get the expectation of Poisson distribution as lambda. Now let us find the variance. This is the formula for variance. You know the mean of Poisson distribution. We have to find out e of x square, and this is the formula for expectation of x square, that is x square into probability, and replace probability p of x. Before that you have to replace x square by x into x minus 1 plus x. We have done the same type of a rearrangement while we were deriving the mean and variance of binomial distribution. So here also replace x square by x into x minus 1 plus x. Now split the summations, and you know this summation of x into p of x is nothing but expectation of x. Now replace that by e of x, and what is e of x? It is lambda. Now you can substitute p of x and then put the limits for x. So in this equation substitute p of x, and here x varies from 0 to infinity. Now you know x factorial is nothing but x into x minus 1 into x minus 2 factorial. Replace the denominator by this expression. Now you can cancel x into x minus 1 in the numerator and denominator. After cancelling, you will be obtaining this expression, but you can see the changes of the limit. So here previously before cancelling it was from 0 to infinity. After cancelling, it will become now 2 to infinity. Now you can take this e raised to minus lambda as a constant outside. Now you can expand this summation. 2 minus 2 factorial is 0 factorial, and you know 0 factorial is nothing but 1. Now take lambda square, which is common inside the flower bracket outside, and you know the expression inside the flower bracket is nothing but the expansion of e raised to lambda. Okay, replaced by e raised to lambda, and then simplify that further, you will get lambda square plus lambda. Now you can substitute this in our variance formula. This is expectation of x square and this is expectation of x. Now substituting in variance formula, you will get lambda. So now you have concluded that the mean and variance of the Poisson distribution are the same. Now let me teach you the another derivation. Show that Poisson distribution is a limiting case of binomial distribution. Write down the probability function of binomial distribution. From this probability mass function, we are going to derive the probability mass function of Poisson distribution when n is very large. That is, in this probability, we are making n tending to infinity. Okay, so using this probability function, we are going to convert it to Poisson distribution function. Now rewrite NCX using this formula. Again, you can expand n factorial as n into n minus 1 into n minus 2 into n minus x minus 1 into n minus x factorial. Now you can cancel n minus x factorial in the numerator as well as denominator. After cancelling, you will be left out with this expression. Now you can take n common from the numerator terms. From each small bracket, you take n as a common factor. Okay, and you know these small brackets, there are x minus 1 terms. There are x minus 1 small brackets, isn't it? So the common factors which we have taken n will now have the power n raised to x minus 1. Okay, see, n raised to x minus 1 because we have taken n common from x minus 1 small brackets. Okay, you can simplify these two. So you will get n raised to x. Now you know that as n tends to infinity, these small brackets will become 1, because I will tell you as n tends to infinity, 1 by n tends to 0. So 1 by n tends to 0, 2 by n tends to 0, x minus 1 by n tends to 0. So you will be left out with the product of 1s. So the value will be 1 itself. So in this expression, these small brackets become 1. So you will be left out with n raised to x, p raised to x, q raised to n divided by x factorial into q raised to x. Now group these two terms, np raised to x. Now we are going to evaluate these as n tends to infinity. Okay. Now as n tends to infinity, you know that x is a constant here and q raised to x is 1 minus p raised to x. And you know that as n tends to infinity, p tends to 0, because for Poisson distribution, p, the probability of success is very, very small. It is approximately equal to 0. So p tends to 0. So 1 minus 0 raised to x tends to 1. So the value of q raised to x tends to 1. Now as n tends to infinity, from Poisson distribution, you know that np tends to the value lambda. Now we have got the value of np, which is lambda. Q raised to x value is 1. Now we have to find q raised to n. And what is np? It is lambda. From this, what is p? Lambda by n. Okay. Now what is q raised to n? Q raised to n is 1 minus p raised to n, and you know that we are applying limit for n, isn't it? So 1 minus p raised to n. Replace p by lambda by n, and this is nothing but it is a limiting form of e raised to minus lambda. You know this limit of n tends to infinity, 1 minus lambda by n, the whole raised to n is e raised to minus lambda. This is a standard formula. So I am going to replace q raised to n by e raised to minus lambda. Here you know np is lambda, q raised to n just now we have got, it is e raised to minus lambda, and q raised to x is 1. After replacing all these, we get the PMF of Poisson distribution. I hope you have understood this. Thus, we can show that Poisson distribution is the limiting case of binomial distribution. Thank you.